Ah. Hello, everyone. Hope you're doing well. And let's do the last part of the chapter, Chemical Equilibrium. Let me share screen. So we did quite a lot about finding the equilibrium constant and then how is equilibrium affected by different conditions. Today we are going to barge on the topic which talks about disturbing and restoring equilibrium. So let me put it on a slideshow and keep going. Now, once a reaction is at equilibrium, we know that the concentrations of all the reactants and all the products are going to remain constant throughout. But what if you disturb the conditions? If you change the conditions at equilibrium, what is going to happen? Reaction will always try to restore its equilibrium. So if you change the concentrations, if you change the temperature or the pressure, it's going to work itself to restore its own balance. Okay? And this is given by something known as Le Chatelier's principle. Now, Le Chatelier's principle guides us in predicting the effect of various changes in conditions that we have on the position of equilibrium. It states that if a system's equilibrium is disturbed, then the position of the equilibrium is going to shift to in order to negate or minimize the disturbance. What are these disturbances? We might change the concentration of a reactant or product, we might change the volume or pressure, or we might change the temperature. So I have made another slides which are clearer than this, but let me start with an analogy with these current slides and go over to that. Now, the analogy would be population changes. So let's consider two countries, which are country A and B. Say their populations are in equilibrium, and say people are moving across the two countries, the emigration rates between two countries are equal, so their population stays constant. Consider a situation in which the birth rate in country B increases and it disturbs the equilibrium established between country A and country B. And here you see that the birth rate in country A increases, so now there are more people in country A, and so the resources of countries A are depleting fast. So what would people do? They would move more to country B. So people will be moving from country B. Sorry, country B has increased, so people will be moving from country B to country A faster than the people moving from country A to country B. So this will continue till all the resources are balanced and a new equilibrium between the populations is established. You understand that the new equilibrium is going to have populations that are different from the previous numbers, right? And so the numbers is going to change, but still there would be an equal distribution that they are going to maintain. It is similar to adding reactant to an equilibrium, like we are disturbing that, we are increasing the reactant and seeing what happens. How does the reaction balance it? So, how will this affect the rate of the forward reaction? How will adding a reactant will affect the rate of a reverse reaction? And how will it affect the equilibrium constant? So now I will go over to a clearer slides which I have made. They are crisper and clearer. So let me go over to that. So what I'm going to do is going to introduce to you these contents, which is defining Le Chatelier's principle, using Le Chatelier's principle to assess effects of changes in concentration, pressure and volume, temperature, and addition of catalyst on a reaction at chemical equilibrium. Okay. So Le Chatelier's principle is named after the French chemist Le Chatelier, who is associated with chemical equilibrium. So he gave this principle. And chemical equilibrium, as you know, that in a reversible chemical reaction, when a balance between forward and reverse reactions attains a condition when no net change in the amounts of reactants and product occurs, then we say that the reaction has attained a chemical equilibrium. For example, you've seen many reactions in our previous classes. This is an example in which the reaction has attained chemical equilibrium. What does Le Chatelier's principle do? It would help us predict the direction in which an equilibrium is going to shift when you change the concentration, pressure, volume, or temperature. Now, I would define Le Chatelier's principle in the following manner. If we apply an external stress to a system at equilibrium, the system adjusts in a way such that the stress is partially offset as it tries to re-establish equilibrium. Now, the words here, the external stress, system at equilibrium, adjusts, and stress is partially offset, and re-establishing equilibrium concepts are important when you write the definition of Le Chatelier's principle. You could express them in your own words, but make sure you convey the idea right. Okay. Now, what do you mean by stress? It's not the stress that we use in day-to-day life. Even there, as humans, when we face stress, we also try to re-establish our equilibrium through meditation, pursuing our hobby, or talking to a friend, like pouring down the everyday thing. So everybody tries to establish their equilibrium in the universe. Okay, so reactants are no different. Now, by the stress here in this definition, I would mean a change in concentration, pressure, volume, or temperature that would remove the system from equilibrium state. So let me now put it down in a slide, and let me say that we are going to assess the effects of the following changes on an equilibrium reaction, which is A, concentration, B, pressure and volume together, C, temperature, and D, addition of a catalyst. Let me go ahead step by step and start with changes in concentration. For this, I have taken a sample reaction in which let's consider the dissolution of iron thiocyanate. So this is iron and SCN is thiocyanate. So I would say this is the dissolution of iron thiocyanate in water, and that produces hydrated FeSCN2 plus ions. How does this reaction happen? So when it produces hydrated FeSCN2 plus ions, that further dissociates into Fe3 plus and SCN minus ions. To tell you, the hydrated FeSCN2 plus ions are red in color. The Fe3 plus is pale yellow, and thiocyanate ions are basically colorless. So if you have more concentration of Fe-thiocyanate 2 plus ions in the solution, that is the reactant. So let me define the reactant side. So this is my reactant side, and this would be my product side, right? Judging by the colors, if I have more of the reactants, the solution is going to appear red in color. If I have more of the products, I'm going to either get a pale yellow or a colorless color, right? So pale yellow would be the thing if it's moving towards the product side, that means the decrease in the red color, or if it is moving to the reactant side, that is the backward reaction, I'm going to get the solution more in red color. Let me see what happens if I change different concentration. So I would define the changes as stress, and then I would say what is the concentration effect. I'm going to say how is the equilibrium shift of the reaction? What is the visible change? I have also put some photographs for aiding the eye. So say my first stress is I add a lot of sodium thiocyanate. Now what happens if we add sodium thiocyanate? Sodium thiocyanate dissociates as Na plus SCN minus. So let me write down that reaction for you. Na plus SCN minus. As a result, you see that this concentration of thiocyanate increases. So we are increasing some concentration in the product side. So my equilibrium constant is going to be concentration of products, that is thiocyanate and Fe3 plus, by concentration of reactant. So that's going to be my equilibrium constant. So as I'm increasing the product concentration, my equilibrium is going to go backward. The reaction will try to consume the added reactant. So it's going to go from product to the reactant back. And so what you would see is a left equilibrium shift and production of more of the reactants. What happens then to the color? We said that FeSCN2 plus, which is the reactant, is a red colored solution. So you would see that the color of the solution becomes more and more red. The red color deepens, and this is how it's going to look like. I hope you understood this. If you did not, please put your concerns in the chat. I would answer them as soon as possible. And then let's take the next stress. Let's add some amount of FeNO3 3 plus. So when we do that, we are again adding source of Fe3 plus. Take a guess what would happen. So again, we are adding products, okay? If we add products, concentration of Fe3 plus on the product side increases, reaction would try to consume the products. So it's gonna go backward, okay? And so it goes, the equilibrium shifts to the left, reactant is produced. What would be the color change? The red color would deepen, all right? Take a minute, have a look at these 2 points. Okay, we go ahead. Let's take an example where we add something which is different than the reactants and the products. Let me now add oxalic acid. So this is oxalic acid. Now I am adding an agent which is going to react with Fe3 plus. So what happens in oxalic acid case is the oxalate produced reacts with the Fe3 plus. Which side is Fe3 plus in the reaction? You see that it's on the product side. So I'm going to consume some of the product now by adding another agent. If I do that, what is my reaction going to do? It's going to produce more products to negate the reaction, right? So if it's going to produce more product, my equilibrium shifts to the right, producing more of the products. And so what do you think will be the color of the solution? The red intensity will decrease and solution would turn yellow due to these ions, Fe, C2O4, 3 minus ion. So my solution color is going to change to yellow. If you did not follow any of these or you want me to re-explain, please type in the chat. Going over to the next slide, let's look at what happens if we change pressure and volume. The pressure and volume again are 2 very important conditions which control the equilibrium of a reaction. So importantly, you should understand that if you have solids or liquids in a reaction, pressure and volume is not going to affect it. Pressure and volume changes affect only and only the concentration of gases in a reaction. So if you got solids and liquids, do not bother anything about this change. Say there would be no change in the equilibrium, okay? But if you got gases, you need to learn this. Why does it affect gas? Because according to the ideal gas law, PV is equal to nRT. Anyways, you need not remember this, but what you need to remember is greater the pressure, smaller is the volume. So let's consider a reaction which is a gaseous reaction between dinitrogen oxide and nitrogen dioxide. So N2O4 gas converting to 2NO2 gas. Let me introduce to you the stresses, that is the changes that we are going to make. Now gases get compressed, right? So if we have gas in a fixed volume of a container, we press down the piston, the gas gets compressed. So what we're going to do basically is increase the pressure by pushing down the piston and decrease pressure by pushing up the piston, all right? And the last one is we will try to increase the pressure by adding an inert gas that is an external source. So let's go step by step. Let's learn what happens if we increase pressure by pushing down piston, which is there in this diagram. What happens to the volume if we push down the piston in a confined volume? Now, the volume that the gas occupies after pushing down the piston is less, right? So the pressure increases, the volume decreases. What happens to the concentration? The same amount of gas is there in a fixed, lesser volume. What do you think happens to the concentration? The concentration of both gases, the reactant and the product, increases because, the mass per unit volume increases. The volume has reduced, right? So the mass per unit volume increases. So concentration increases. Please keep that in mind. So if you push down a piston, the concentration of both gases would increase. So if the concentration increases, let us write down an equilibrium constant for this. So for this, it would be NO2 gas square by N2O4, right? If this is the case and concentration of both of them increase, so the denominator is going to remain lesser than the numerator always because the numerator is squared, right? What would happen to the equilibrium? The reaction would try to produce more and more of the reactant. And so until QC is equal to KC, the reactant will shift towards left. That's only because here I have a square in the numerator while I do not have that in the denominator. If there was no square and we were doing the same thing, then there would be no change in the equilibrium constant. Okay. What happens if we decrease pressure? Now, if we decrease pressure, we are expanding the volume in the same thing. We are decreasing the concentration of both gases. When that happens, more and more of the product will be formed till QC is equal to KC. Take a minute to think about this and type in the chat if you need any more clarification on this. Okay, if you have no questions, then let's try increasing the pressure by adding helium, which is inert gas. So He stands for helium. And now we are adding more gas in the same volume. So what happens? There is no concentration effect because the concentration of those gases remains same, but you are going to increase the pressure by adding extra things into the same volume. What happens to the equilibrium shift? No effect because the concentration does not change. If the concentration does not change, you don't need to worry about the equilibrium constant. Right? Simple enough. Let's look at temperature changes now. So change in temperature would alter the equilibrium constant. Remember, equilibrium constant is defined at a particular temperature. So if you change the temperature, it's going to change the equilibrium constant itself. Now, pressure and volume would change only the equilibrium position. So here there are more changes. The numbers change. All right. So let's consider a reaction in which, again, N2O4 goes over to NO2. We said that the K for this would be NO2 gas square by N2O4 gas, right? Now, this reaction is an endothermic reaction, the forward one. That means the forward reaction happens with absorption of heat. So when you provide heat to the reaction, only then the forward reaction is going to happen. So if the backward reaction has to happen, it would be exothermic. So it would release heat. We know that delta H naught for a forward reaction would be negative of that for a backward reaction. So I have written down the values for you. For this particular reaction, for the forward reaction, that is decomposition of N2O4 to NO2, you would have delta H naught as 58 kilojoules per mole, while for the backward reaction, which is an exothermic one, you are going to have delta H naught as minus 58 kilojoules per mole. Make sense? All right, let's apply stress now. So there would be obviously two stresses in this case. One is increasing the temperature. The second would be decreasing the temperature. Now, if we increase the temperature, which reaction would be favored? The endothermic or the exothermic? Simple analogy, endothermic would be favored because endothermic requires heat, right? So if we increase temperature, the forward reaction would be favored. If the forward reaction is favored, then the equilibrium shift will be to right, and more of the product is going to be formed. Agreed? So NO2 increases, equilibrium constant Kc increases. Now that's an important point which we did not find in the other two because temperature changes actually change the Kc. So you will be asked whether the equilibrium constant Kc increases or decreases. If it increases, to what values? If it decreases, so what is the new value? These could be the kind of questions which could be asked here. Okay, so be ready for that. Let's take a case in which we decrease the temperature. So if we decrease the temperature, exothermic reaction is going to get favored. So I'm going to favor the backward reaction. When I'm going to do that, the reactant is going to be produced. So the concentration of N2O4, which is the reactant, is going to get increased, right? And so what happens to Kc? N2O4 is in the denominator of the reaction, of the equation. So my Kc is going to decrease if the denominator increases. Take a minute, have a look at this, make sure you're good with this. If not, please let me know. Okay, I hope things are fine. Let's go over to the last slide in this, which is the effect of catalyst. Now, catalyst is another thing which can affect the pace of a reaction. So what happens when you add a catalyst to a reaction? It basically lowers the activation energy of the forward and backward reaction. And remember, it's to the same extent. So if something is, in the backward side and in the forward side is done to the same extent, what would happen to the equilibrium? No change. So there would be no change in the equilibrium constant, no change in the equilibrium position. Please remember, this could be a trick question for you. We could ask you whether I add a catalyst and then what is happening to the equilibrium constant? No change because it's doing the same purpose in both sides, okay? And here I've shown a profile of an uncatalyzed reaction, which is going through a higher energy barrier. So this point is called energy barrier. And the catalyzed one, which goes through a lower energy barrier. So you see that the y-axis reads energy, all right, and the x-axis reads time. But what is the overall effect? Adding a catalyst would only cause equilibrium to attain sooner, okay? Because energy barrier is lower, but there would be no change in the equilibrium constant, no change in the equilibrium position. Got it? I have a few practice questions for you, which you could go through and try to answer later, whenever you have time. Let me go over the old presentation and see whether we have something more, any conceptual questions which I would like you to answer. So this is what we discussed in the other one as well. We do not have anything more here. Yes, you could try answering this. Consider the exothermic reaction where 2NO plus Cl2 gives 2NOCl gas. Which change causes a reaction mixture at equilibrium to shift right? Would it be adding NOCl to the reaction mixture? Would it be increasing the volume of the reaction vessel at constant temperature? Would it be increasing the temperature of the reaction vessel or none of the above? Please try to answer this and type your comments in the chat. Type your answers in the chat. Please read it really carefully. We have gone through all the factors now. So adding NOCl is going to increase the product side, the reaction is going to shift left, right? What about B? What about C? What about D? So my answer would be none of the above. All the things that I'm going here, A, B, C, is going to cause the equilibrium to shift right, not left. Okay. So my answer would be none of the above. That's it in this chapter. So let's now just revise this chapter and go over it. Like, what did we do from the beginning? Just a brief revision so that you're good with this. And an assignment would come up soon, which you need to answer. So we learned about equilibrium, dynamic equilibrium, reaching equilibrium, and then we said how to define an equilibrium. It's not same as equal. It's when the rates of the forward and reverse reactions are equal at equilibrium. So we did these analogies of population changes, and then we defined something called equilibrium constant, and we defined law of mass action. Then we tried writing equilibrium constant expressions for different reactions, where there are gases, where there are solids, where there are liquids. And we said, what does this value of K imply? How are Ks related for related reactions like forward and backward? When a reaction is in stepwise, how do you write that? And then we learned the concept of Kp as an equilibrium constant for reactions which involve gases. Okay. And how is Kc related to Kp? So Kp is Kc to the in multiplied with RT to the power delta N, where R was the gas constant, T was the temperature, and delta N was the number of moles, right? So now we skipped over this slide because derivations are not there in your syllabus. Don't need to worry that. But units of K conceptual questions here, and then we described heterogeneous equilibria, and we went over initial and equilibrium concentration for reactions at a fixed temperature. We said that even if we start with different concentration, the equilibrium constant is going to remain same until and unless you change the temperature, right? We spoke about stoichiometry, the reaction quotient, which is QC. And we said if QC and KC are different, then the dynamic equilibrium tries to re-establish itself, and you have a direction of change. Moving further, today we saw the Le-Chatelier's principle, where we disturbed and restored the equilibrium. That's it in this chapter. Not a very short and sweet chapter, but you need to study a lot. But it's like very conceptual and it pertains to a certain concept. Okay. So it's not too much. Just make sure you understand all the concepts well. You know how to write the equilibrium constants. You know how to interpret the things like changes in concentration, changes in temperature, etc. If you know that, you know this chapter. Okay. So that's all in this chapter. An assignment would come up soon. Please answer that in time and make sure you have understood everything. If you not, please do message me and please do email me your concerns. We can put up a session as soon as possible. Okay. Thank you. I would stop sharing and stop recording now. Thank you for joining me in this session. Bye.